Okay, so the above were examples where we were using something called explicit differentiation. So that is the function y is directly expressed in terms of the independent variable x. So in other words, y was isolated for us. It was a y equals something. Whenever it's just y equals something, there's no other y's. It is easy. We can do the explicit derivative. But can we find the derivative of a function when y is not isolated? So looking at exercise 1 here, it's not that big of a deal. This is just bringing us back to grade 9 math, where I could rearrange that equation. So I could take this equation and I can write it as 7y is equal to, as I move things over, it would be negative 4x plus 14. And then I'm going to divide everything by 7. And I'm going to be left with y equals negative 4/7 x plus 2. Right away, I can see I can actually take the derivative of this. It's just a simple little derivative, and it'd be easy to go. All right, so bring the exponent down. So bringing the 1 down and timesing it by the negative 4/7, and then subtracting 1 from the exponent, which would give me a power of 0, which is 1. So I'd be done right there. So that's one case. That's kind of the easy case where I can rewrite my equation so it says y equal. Then I'm able to take the derivative. What about something that's a little bit more complicated? Like, can we determine the derivative of x cubed minus 2x squared y plus 6y squared minus y cubed? Yes. You can't really isolate the variable, the y there, too easy, but there's got to be a way to take the derivative, and that's where we use implicit differentiation. So implicit differentiation is a method for finding the derivative when one or both sides of the equation have two variables that are not easily separated. So we're going to take the derivative of both sides of the equation. In this case, there's no equal sign, but it would be equal 0. But we just take the derivative of everything. So we don't have to solve for y. So I just want to kind of do a basic little example here. And I want to determine the derivatives of 4x to the power of 3. So really super simple kind of power rule one here. So how do we find the derivative of this? Well, we bring that 3 down, and then we multiply it by the 4. We leave the x the same. We subtract 1 from the exponent. And what we're kind of doing here, but we haven't thought about it, is we're timesing this by the derivative of x. But the derivative of x is kind of like 1. You'll see why that matters in a minute, but we don't normally write that 1. But we are kind of doing power rule, so we bring the 3 down, multiplying it by any constant in front, leaving the x as is, subtracting 1 from the exponent, but then we are kind of taking the derivative of x, which is 1, and multiplying that at the end. That might help some of you with the chain rule, and really, we're going to do the chain rule here. So we have 4y cubed is what we want to take the derivative of. So I just started by rewriting that as 4 and then y in brackets with the 3 up above, because now it does really look like a chain rule. So my derivative of this one, I almost wrote y prime equals, but I'm not doing that anymore right now. I'm just going to bring that 3 down, timesing it by the 4, leaving the y as is, subtracting 1 from the exponent, and then I'm taking the derivative of y. Well, we haven't used this notation too much, and I could put a y prime there, but the more common notation is dy by dx. That is the derivative of y. If you think back to other questions when we had something like y equals 3x plus 1, we usually used y prime, but the other way of writing that would be dy by dx is equal to 3. And there is, you can see the derivative of y is dy by dx. So in this case here, we use the chain rule, bring the exponent down, multiplied it by the constant, and then we just multiply it by the derivative of what's inside the brackets, which is the y. So we just write it as dy by dx. Okay, that's kind of the idea of implicit differentiation. So it was kind of a simple, not really much of an equation, but we'll get to an example where it will work. So what are the steps to implicit differentiation? Well, we're going to differentiate each side of the equation by treating y as an implicit function of x. So this means we can use the chain rule on terms that include y just by multiplying whatever we do by dy by dx. Once we've taken our derivatives, then we just have to solve or isolate for dy by dx. So this will make a little bit more sense as we do some examples. And I kind of have two examples here to work on. We have x squared plus y squared equals 100. So let's go to zoom in here. I'm going to start with this one here. So we just start taking derivatives. So derivative of x squared is 2x. Then we're going to use kind of like that chain rule on the y squared. So we're going to have the plus, we bring the 2 down, we leave the y, we subtract 1 from the exponent, but then that new thing that we're going to be doing is we're going to be timesing that by dy by dx. Kind of like treat that y like it's a bracket. There's brackets around that y. And the last thing we do is multiply it by the derivative of what's inside the bracket. So we're just writing it by dy by dx because that is the derivative of y. That's what dy by dx means. Derivative of y in terms of x. So we'll go back to our equal sign here. And the derivative of 100 is 0. So now that I've gone and I've differentiated each term, I've got to isolate that dy by dx. So I'm going to keep that on the left side. It's timesing it by 2y. So the first thing I'm going to do is move that 2x to the other side. So I'm going to have 2y times dy by dx equals negative 2x. All right, I'm almost there. Last thing I have to do is get rid of that 2y in front. So we should be remembering, just like we did up in some other examples, we can just start dividing both sides by 2y. So that is going to give me that dy by dx is equal to negative 2x over 2y, or we can even just cross out those 2's and say that it's negative x over y. So it's a little bit different now that our derivative of the function is negative x over y. So we're going to have some y's in our derivatives now, but we're moving past polynomials. We're moving into more advanced derivatives, so it's okay to have that. So my derivative of x squared plus y squared equals 100, so that's my circle. X squared plus y squared equals 100 is a circle with radius 10. I was able to take the derivative of that circle, and the derivative of that circle, dy by dx, is negative x over y. So let's look at another example now. And let's look at this one that's a little bit longer. We're going to have a couple of dy by dx's in this. But let's just go ahead and work on this one right here. So 3x cubed plus 6xy plus 2y equals 99. So remember, the first thing we're going to do is just start taking derivatives. So the first little bit is easy. That's just a simple power rule. So we can bring the 3 down, multiply by 3 to give us 9. We leave the x, we write it as a squared. That's an easy one. But in the middle here, it's really 6x times y. So we actually have to use the product rule here. So the product rule says f prime times g plus f times g prime. Okay, so f prime, so the derivative of 6x is 6, times that by my second kind of part, which is the y, that's my g. Then I'm going to be adding f, which is 6x, times the derivative of the second thing. And remember, the derivative of y is dy by dx. Now we've got the derivative of plus 2y. Okay, so this kind of says, think about that chain rule again. Bring that exponent down to 1, times it by the 2. Leave the y as is. Put it to a power of 0. Because I subtracted 1 from the exponent, and times that by dy by dx. Then we have equals, and the derivative of 99 is 0. So remember, the derivative of any constant is 0. So there's kind of my first step. We use the power rule with a 3x cubed, and we got 9x squared. We use the product rule in the middle. So we took the derivative of 6x, which is 6, left the g, or the y, as is. Then we added, leave the 6x as is, times the derivative of y, dy by dx. And then the last little bit, we had to use kind of like a chain rule again. And really remember that y to the power of 0 is 1, so that's really good to be gone. But you can see now we have two dy by dx's. Not a big deal. We still start by moving everything that does not have a dy by dx to the other side. So I'm going to move the 9x squared to the other side. I'm going to move the 6y to the other side. So on this side, I'm going to have 6x times dy by dx plus 2 dy by dx is equal to minus 9x squared plus, minus 6y. Okay, so I can see kind of a common factor on the left-hand side, which is that dy by dx. So let's common factor out that dy by dx. And then what's left when I take the dy or factor the dy by dx out? This could have a 6x there, and I could have a plus 2 there. And yeah, I might be able to do some simplification on that bracket, but I'm not worried about that yet. And I'm going to keep that as my minus 9x squared minus 6y. And then you can kind of see here, okay, well, my dy by dx is almost isolated. So all I really have to do is divide by 6x plus 2 on both sides. And then I'll have my dy by dx isolated. Okay, so dy by dx is equal to minus 9x squared. Don't know why I always want to write a plus there. Minus 6y all over 6x plus 2. So if I do want to write this in simplified factored form, I should go ahead and just kind of look for any kind of common factors, anything we can take out. So my dy by dx, I can see on the top there, I can take out a minus 3. Okay, if I take out the minus 3, I'm going to have 3x minus 2. And on the bottom, I can see I can take out a 2. And I'm going to have 3x plus 1. And there's my derivative in a simplified factored form. So I'm going to stop here, and I'm going to get this one saved and uploaded, and we'll keep going.